Alright, geometers, today we are going to be talking about biconditional and definitions. So today we're going to recognize and use something called a biconditional statement. So our first line of business here is to write the following statement in if-then form as a condition, and then we're going to flip it and we're going to write the converse. So let's just refresh ourselves that the converse is the reverse of the if-then, where we switch the hypothesis with the conclusion. So generally speaking, since this is my subject, perpendicular lines, and here's my predicate, are two lines that intersect at a right angle, generally what we can do is just turn the if perpendicular lines, or say something like this: if two lines are perpendicular, and I'm going to use this symbol for perpendicular, and then the predicate can be the conclusion. Then the lines intersect at a right angle. So if two lines are perpendicular, then they intersect at a right angle. So what is the converse? Well, we just flip those two pieces. If two lines intersect at a right angle, then they are perpendicular. So what are perpendicular lines? Well, we can draw that real quick. We know that perpendicular lines look something like this, and it doesn't have to be an upside down T. They can be crosshairs, they can be anything like this, as long as we identify it with a right angle in there. So how would I write that though? L and K, so these are my two lines, and I can say L is perpendicular to K. So notice what's happening here. In this situation, we make a statement. Perpendicular lines are two lines that intersect at a right angle. And if I write the subject as the hypothesis and the predicate as the conclusion, and then we write the converse, notice that in our heads, we're saying, oh, that thing is true, and that thing is true. So this brings us to our topic at hand. There's a word which your spell checker will often say is not a word, but it's called biconditional. So if we word dissect that, bi of course means two, and conditional means if then. So a biconditional statement is any statement that contains the phrase if and only if. So biconditional statements can be broken up into two conditional statements. Of course, the first one is simply an if-then statement, and its converse. Now, I know the first thing we want to think about is, oh, is this true? Is this true? Is it false? Is it false? Notice that it does not matter if it's true or false at this point. If you see the phrase if and only if, it is a biconditional statement. And whenever we see if and only if, we can split it to an if statement, if then, and a converse. Then what we can do is talk about true false after that. So we could have a true biconditional statement, or we could have a false biconditional statement. But what makes it biconditional is if and only if, and nothing else. So let's write this biconditional statement as a statement and its converse. It is Saturday, if and only if. So because I see the if and only if, I know it's a biconditional statement. Again, we're not thinking about true false, we're just thinking about form. I do not have to go to school. So my original statement, my if-then statement, the easiest thing to do is just to delete this, the if and only if, and put the word then in front, and attach the if in the front. And so now we have, if it is Saturday, then I do not have to go to school. Of course, the converse says, let's just flip those two statements, the conclusion with the hypothesis. If I do not have to go to school, then it is Saturday. So in this exercise, all we did was take the biconditional statement, because it has if and only if, we split it to an if-then statement and its converse. Again, we are not analyzing true-false yet. You can, but you don't need to. So in example number 2, we're going to write the biconditional statement as a conditional statement and its converse. So go ahead and take a moment to do that, and then press pause and check your answer in a moment. Now notice when I wrote my biconditional statements into a conditional statement and its converse, essentially I just erased this, put a then, shoved an if in the front. Notice what I did not do. I did not bring the word they over into the hypothesis. Notice if three lines are, if three lines lie. So I took the idea and just made sure I was grammatically correct. So if three lines are coplanar, then they lie in the same plane. And when I converse that, if three lines lie in the same plane, then they are coplanar. So make sure we establish the subject before we use our pronouns. All right, on page 2 here, we're going to now get into true-falseness. So we're going to check the validity of this statement, so by deciding if it is true or false. When I say if it is, I mean the biconditional statement. The whole biconditional statement has to be true, or can be true, when both the converse and the initial statement are true. So again, when we convert this, all I have to do is convert the if and only if to a then, and put the if in the front. And if x equals 3, then x squared equals 9. So how do I know if that is true or false? Well, so we're given that x is 3, so now let's put 3 in. 3 squared is 9, so we see that this is indeed true. Now what's the converse? It says if x squared equals 9, then x has to be 3. And we think about that and we say, well, it is true that if I put 3 in, I get 3 squared, I get 9. But is there another number? And the answer is yes, there is another number, because x could be negative 3. So this here would be my counter example to the converse. So what's my conclusion of the matter? Since my original statement, when I split the biconditional into two statements, my original is true, my converse is false, that means this biconditional statement is false. So biconditional statements can be either true or false. In order for a biconditional statement to be true, both the original statement and the converse must be true. If not, then the statement is false. So the only way for the biconditional statement to be true is if both the original statement and its converse is true. Now it turns out that a good definition can be written only as a biconditional statement. That's how we know it is a good definition. So take a moment now to do example number 4. Rewrite in if-then form, then write the converse. If they're both true, then write it as a true biconditional, if and only if. If it's false, then just provide a counterexample. So all dogs are canines. So again, our subject is dogs, our predicate are canines. So let's turn that in. If an animal is a dog, then it is a canine. We can analyze this. If an animal's a dog, then it's a canine. True. The converse of that. If an animal is a canine, then it is a dog. Now, analyzing this statement is a matter of debate because it depends on how you interpret the word dog. However, the most straightforward reading of dog is a pet dog, a domestic dog. So if an animal is a canine, then it must be a domestic dog, and the answer to that is false. Why? Because it could be a wolf or a fox. So, but if we just read this as dog synonymous with canine, then we could pause and say both of these are true. Now take some time to look at page 3, examples 5, 6, and 7. Then check your work in a moment. So in this counterexample here, angle 1 and angle 2 do share this side, although angle 2, that's not the only part of that side. There's a little bit more to it, but it's shared. It's still overlapping there. So the key about adjacent angles is that they share a side and a vertex. So this vertex, if it were shifted down, then angles 1 and 2 would be congruent, adjacent. So here's the converse, and of course, any angle that's obtuse but not 94 degrees. So for example, this here is 135 degrees, and it is obtuse but not 94 degrees. So this would be my counterexample. And now this last one is not very clean, but the perimeter of a triangle can be found if and only if you add up the lengths of its sides.